Yes, thank you.
Go ahead.
Yeah, so I will be quick. This is a last presentation, and also it's a small project. It's a kind of pilot project. So the PI of this project is Jaydev Rajagopal from Noir Lab. So they built an instrument called NUID, a spectrometer, to characterize exoplanets in the visible, and it is installed at Wayne 3.5 meter telescope at Kitt Peak Observatory. So their main goal is to determine orbits and also spin orbit alignment in close planets. Also, but the primary goal is to characterize exoplanets and find out Earth-like planets or habitable zone planets. For that, they want to have precise and accurate radii around 1% level. For measuring the habitable zone, we need to know the temperature very accurately. That depends on the radii of the star. So that is the science goal. So they want to measure the diameters, and they looked at the different beam combiners, and they asked me for help. And then so this is the chart. This is the paper we looked at in the beginning. So there is these are all the CHARA, not all, maybe a few, I think. This is the paper Tyre et al. 2021. They compared the diameters measured with a few beam combiners at CHARA, and they found out that there is a 4% of systematic error in the radius. So we thought, let's try with MIRC-X, and since MIRC-X will measure the 15 baselines at a time simultaneously, so probably we can do reduce the systematic errors. We will see whether MIRC-X can do better job or not. So we spent 2 nights of observing with MIRC-X, and in total 6 targets observed, but only 3 targets are observed independently on different nights. So I will show you 3 targets, how they how MIRC-X showed the radii, and one of them is kind of a reference to make sure that to compare with other beam combiners or to compare with the literature. And this one is, first one is GJ411. This is a exoplanet host candidate, I think. So this is 1.4 radii of the diameter of the star. And so we observed 2 nights. Our observing strategy was that similar to Pavo. So we wanted to go quickly, go to the star, and then calibrator and go to the star. And so we took off data than normally MIRC-X on standard observation do. So in order to quickly slew to the calibrator, we took that approach. In order to that will help to that will help to mitigate the atmospheric turbulence calibrations between the calibrator and target. And we measure the angular. This is the this is UD. It's not the limit darkening corrector diameter. Uniform disk. So this is 1.3758 one night and 1.3780. So if I compute the percentage error, this is less than 1%. And if I compare that diameter with literature, it matches with classic and PTI measurements in the past. And then the second star, which is 1 milliardsecond diameter. So this is one observation, the second observation, and we see that there is a, I'll come to here. So we see this is the measurement 1.0346 in diameter, uniform disk models, 2 different nights, and we measure 1.4 accuracy across different nights. The precision is okay. The same night it is calibrating, but across night it is giving more than 1%. So I went into the data, and we see that so the problem is that the visibilities are kind of offset or dropped on some occasions, which is problematic. That is causing the error in the accuracy. And one of the thing with MIRC-X is that the error in the visibility precision is very small than like in the similar previous presentation. The error bars are smaller than the offset here. So that is the limitation, or maybe we are underestimating the errors. So this is a second target, and then this is a smaller target, which is 0.65 milliarcseconds, and this is a noisy because it's observed with higher spectral resolution GRISM. So it's faint, so less flux, so it is getting more noisy thing. But here you can see the similar thing. So they here I estimate the accuracy error between 2 nights is 1.6. And if you notice, this error is increasing with the star diameter is decreased. That is expected. Like if the star diameter close to the resolution of the instrument, for example, MIRC-X instrument, the angular resolution is 0.5 milliarcseconds. So this star is close to the angular resolution of the star. This star is close to the angular resolution of the instrument, so we are getting higher accuracy, higher error. So one of the I think I would say mistake is that we should have taken more data, which is actually we should have taken like standard observations. Because one of the things I realized that we take on MIRC-X, we take data and backgrounds because it's a near infrared instrument, near infrared camera. So we take backgrounds and then beams. Beams is like we close all the shutters and only open one telescope and so on. So the beams are used to measure the kappa matrix. Is a calibration between the fringe channels and photometric channels. It is a measure of any polarization or other things. So that beams are seems to be not ISNR. So those are contributing some of the visibility miscalibrations, and also other sources can be flux drops, like when we are observing, if there is any flux drops due to any tip tilt problems or AO correction problems, then if you lose flux abruptly, that is also causing the visibility drop. And there can be places on the delay and cart. On some occasions, it can patchy delay line area, so it can make vibrations. Are also on the MIRC-X table. We have situations in the past, but it is now corrected out. So vibrations, but we are now installed accelerometers, and we are now tracking. So these are the reasons that could introduce vibrations. If there are vibrations, fringe contrast will be lower. If that happens on a calibrator, on the calibrator, the fringe visibility will be low. So when it calibrates the target visibility will be higher, and vice versa can happen. That's how there can be visibility offsets. So John Monier is planning to install a 6 telescopes star tracker that will actually help in unifying the flux. So this will help in the future getting the uniform flux. So that will help. And also we are recording metrology data. These data sets we took in 2021 March. So there were no, these tools were not available. So we were not sure what is happening. Now we know these tools are there. So we can compare our data and see if there is a part of the data is bad or something like that. We can remove them. But yeah, one of the, as I said, we took only half the data. That also limited us to select any bad, to remove any bad data in those observations. So currently we have 1.6. This is the limit. This was the limit of the MIRC-X instrument in measuring the diameters. But in future, probably because of the 6 telescope star tracker or other tools might help to improve that one. So when SPICA is ready, probably no one is interested in using MIRC-X for measuring diameters, but remember that MIRC-X is the fringe tracker for SPICA. So you get free data when you are operating with SPICA. So so you can use both MIRC-X and MIRC-X and SPICA data both for measuring the diameters and the limb darkening observations. Thank you.
Thank you, Narsi. Do you have questions in the room? Okay.
Hi, Narsi. It's Gail Shea from the CHARA array. So thanks for this careful work on looking at the systematics. So based on your analysis here, do you, instead of taking these short 5-minute sets for your diameter work, do you recommend going back to the full 10-minute sets to improve the calibration?
Yes. Yeah, I think MIRC-X likes the standard one. Yeah, as you say, we should take full beams. You can reduce the data. I think that's okay, but not the beams.
Are there other questions? I see that there is nothing in the chat. No. I wanted to ask you that the differences between two nights could be due to stellar activity, but I saw that since the visibility curve is there is an offset with between the curve and the point, I think it cannot be related to stellar activity, right?
I think no, they are sorry. They are clearly seen that there is a offsets. I don't think they are coming from, for example, this point here. and this one are the same baseline, this gray one. I don't think this is any astrophysical.
Yeah, I agree. Okay, so if there are, Stefan has a question.
Yes, Stefan Kraus. And Narsi, I was wondering whether some visibility offsets that you show here, whether these are the problems that we sometimes see with the S telescopes, where we know that it's a systematic problem, or is that kind of the general accuracy floor for all baselines that you see there?
Yeah, yes, one problem, we have a particular region where we see that one. This one is, no, it is, yeah, so even normal observations, yeah, for example, YSO observations or binary observation, we see sometimes occasional visibility drops, but those observations not hugely affected because of that one. Binary is not, or YSS can afford like 5% visibility drop. So I think those are people are using like that, but when we use it for these radii measurements, we need very accurate ones. Yeah, so I think there is no the only so far my understanding is that beams are helpful, that I already simulated that on STS, the 6 telescope simulator in the lab. But the vibrations, and I also simulated the flux drops caused by the beam drifting, that I played with the STS flux and tried to reproduce that. So it is also affecting the visibility drops. So yeah, uniform flux is always helps. So I think the STST you are bringing, that might help for MIRC-X.
Thanks.
So if there are no more questions, I think we can thank Narsi again and all the speakers of this session.